So welcome to this week's SPCL cast. I'm Thorsten Höpfer from ETH Zurich, and I'm super happy that we could convince Dan Ernst to speak to us today. Actually, Dan and I are going back quite a long time by now. We're even overlapping at two different companies, like both Cray and Microsoft, and we just chatted about old supercomputers. So, but I would like to give the stage to Martin now, who introduces Dan a little bit more formally, and then, of course, having Dan give the talk.
Thanks, Thorsten. Dan is currently a principal architect in Microsoft's Azure hardware architecture team, where he leads research on future memory systems. Prior to joining Microsoft, Dan spent 10 years at Cray HPE, where he was part of the team that architected the Department of Energy's Frontier and El Capitan Exascale systems. Dan served as part of multiple industry standard bodies throughout his career, including the CXL, CCIX consortia, and as a founding board of directors members of the Gen Z consortium. And in case of any questions during the talk, please leave them in the chat, and we will have a QA session afterwards. Thank you again, Dan, for being with us. And without further ado, I leave the stage to you.
Great. Thanks to both Thorsten and Martin. I appreciate the request to come talk. It's always fun to come and just sort of tell some stories, but hopefully help learn a little bit of insight into what the industrial side of a lot of the sort of pathfinding and architecture tends to look like. So as Martin mentioned, I'm currently at Microsoft Azure, but before that, I did spend 10 years at Cray and a year by acquisition at HPE. And the first thing I did there, really a lot of what I did was I worked on pathfinding for node architectures, so compute and memory systems. So I was the PI for our Fast Forward 2 and Path Forward programs focused on those kinds of technologies. I worked on things like the ARM scalable vector extensions and the HBM memory spec and things like that. And those programs touched a lot of things that eventually worked their way into Exascale systems, right? And so I did work then as part of the team working on systems, architecting systems like Frontier, El Capitan, which I'm super excited to see come to fruition. I actually got to visit El Capitan last summer, the rock, not the system, but not far away actually. But really, I spent a lot of time on the design and optimization of what I would call unique or leadership class systems, right? And then about almost 2 years ago now, I flipped the switch and decided to try some different problem sets. So I moved over. I'm now at Microsoft, and I'm in a team called Azure Hardware Architecture, which is run by Steve Scott, who many of you may know. But I'm working for Mark Hill in a pathfinding organization, and specifically leading a team looking at memory systems and memory architecture. So what's interesting between these two jobs is dealing with memory systems at Cray and dealing with memory systems at Microsoft. It's a lot of the same technology. It's a lot of the same people across the industry, but it's a very different collection of problem statements. And so it's interesting to sort of take a different look at the technologies that I've been working with and how they fit into a different context. And I'll talk about that a little bit as we go today. So what are we going to talk about? I titled this talk, Memory-Centric Designs for Modern Data Centers. And I want to start by, kind of saying, okay, what do I mean by memory-centric? That's a phrase that's been used many times, and I would argue that the way that I use it is probably different than most that you've heard. And then I want to talk through sort of the way that I think about that as it applies to a couple of these different problem statements, right? One of them being exascale supercomputing, and the second one being sort of resource management in cloud data centers. So sort of one from the old job, one from the new one. So let's start by memory-centric architecture, right? You may have seen memory-centric architecture illustrated as a architecture where the memory is at the center of the system, right? Meaning that the connectivity graph drawn of the system has memory at its core and sort of the compute pieces at the outside, right? And this comes, from a common view of it. This one comes from Kim Keaton, a former colleague at HPE, but I'm going to argue that my statement of memory-centric architecture does not mean this, right? Just to clarify, this is not where I'm coming from. Where I'm coming from is a little bit a different perspective, and it's really more that I come from actually a microarchitecture background. My doctorate's in dynamic scheduling, but I wanted to think about architecture as an active thing, a verb, right? So memory-centric architecture to me means a process in which memory capabilities and requirements are a central consideration in design choices, right? That we need to be thinking about how memory and data is used and use that as a driver for the architectural choices we make, as opposed to having it be a secondary or afterthought view in system design. So just to outline sort of a basic process for how to do this, right? If I'm going to do something that's an application or workload optimized memory system, there's sort of three things that we've learned over the years that we need to do. All right, one, we need to learn the common data patterns and the requirements of the workload, right? What does the workload do? Where is the data and how does it move, right? And then we need to figure out how to measure that, right? The second thing we need to do is then, with that understanding, really focus on the memory technologies and architectures that match those patterns of the workload most closely, right? Now, I'll note that as somebody in industry who often as a system vendor, we get vendors coming in trying to tell, hey, we have this technology, would you consider it? And they're often motivated by graphs like these, right? Here is a triangle, right? We're all familiar with the triangle of memory systems, right? Where you have the small, fast thing at the top, and then as you go down, it gets larger and cheaper per bit, for example, but also slower, right? And more power hungry, right? And what's interesting is I would get these pitches based on, here's this triangle, and there's a gap in this triangle. So we're going to try and fill that gap, right? Now, from a supply side perspective, trying to fill a gap, it's a crudely in a crudely defined hierarchy is a reasonable absent other data, right? But if you go and look at which of those technologies actually succeeded, it was not the ones that their target was filling the gap. When push came to shove, the ones that won and got scaled were ones that actually served a workload need, right? They fit somebody's data pattern, right? And a lot of the ones that didn't, right? So the last thought is, in system design, you want to focus your investment. So in modern computing systems, there's an immense number of levels of memory, right? All the way from L0 SRAM caches through multiple levels of DRAM and those types of technologies, through other things, and then into the storage hierarchy, right? And I think the key insight is that a system that can have all of those levels and all those technologies doesn't necessarily mean that it should have all of those levels or those technologies, right? We can skip some. And particularly, you want to use the workload requirements in the first one to really guide you on which ones you want to use actively, which ones you want to skip, right? Because in a world where you're trying to be the most efficient system, you can't spend a whole bunch of extra money on a memory that's not going to really provide a lot of benefit, right? Based on the workload. So I used what most closely matches, and then as little else as possible. I'll talk through examples of this. So let's talk about metrics a little bit. When you're trying to understand the patterns of data in your workloads, what is it that matters, right? So we need to somehow express our workload needs in some set of parameters, right? I think the most important piece of this is that those parameters need to be judged at a level that is full size, right? It's real, and it's not micro-sized, it's not summarized, it's not a kernel, right? It's when I'm running this thing at the full scale that I'm going to run this thing, what are the metrics that I need? What do the patterns look like, right? I've seen many people, for example, use, this is one of the gotchas with a lot of the mini apps and micro apps that you see from trying to drive technology forward and try to drive understanding, is they do drive understanding of some of the patterns, but the patterns live oftentimes in an application that does a lot of other things, and most of the other stuff is data movement. And so that's the part that in the memory world tends to dominate how we think about things, right? So some first order parameters that you could use obviously are performance metrics, bandwidth versus latency, whichever one matters, and then that balanced against sort of the sensitivity to parallelism, right? I mean, bandwidth and latency are related by parallelism effectively, right? We need to look at capacity needs, right? How big are the data sets that need to be in memory, and how are they actively used, right? So what's the size of sort of the hotness domains within that larger capacity size, right? And then the other one is, what is the granularity of data usage at each of those levels in the hierarchy, right? Do I care about one 8-byte thing at a time? Do I care about cache line size? Am I grabbing a data structure that's 4 kilobytes? In which case, maybe I should just use a storage medium, right? Those kinds of questions can lead and have trade-offs within the technologies that we can sometimes leverage to great effect, right? And there's others to consider that are what I would call, people think of them as ancillary, but are important to consider. Resilience and reliability requirements, right? And then the needs of data precision, right? What do I care about? What data type, right? Now, can we move that, because that has impact on both data movement and storage, right? So these are the sorts of things that we want to be thinking about. And again, you want to be thinking about these at the system level. So if I'm measuring latency, for example, and I'm talking to DRAM people, they're going to ask about like, what do you want the TCAS to be, right? Like that's not my metric. My metric is load to use, or my metric is throughput of a lot of latency sensitive software, right? Okay. So this is just the general concept, right? What do I mean when I say, memory-centric architecture, right? Thinking about memory systems holistically and quantitatively, and then trying to make decisions and guide yourself in a pathfinding effort towards what you think is going to be the best architecture. So with that as sort of our first order framework, let's look at a couple of examples of how to apply this and how we've looked at this in the past. The first context we'll look at is Exascale. And so again, this started, if you want to take a checkpoint, right? Fast forward to, we were working on this sort of pathfinding effort in about 2014, right? So I want you to sort of go in the Wayback Machine to 2014, those of you who can, right? At the time, there was no high bandwidth memory, okay? Most HPC systems were just rolling out Haswell based with the first DDR4 DIMMs, right? That's what we were rolling out that year, right? And so that's the context of what you should be thinking about as the mainstream HPC systems look like, okay? So in that context, we were thinking about, well, for Exascale, what should this look like, right? And so one of the nice things about my job at Cray, especially at this time, is I was physically sitting in the middle of a giant group of people that worked on applications performance, right? They would do benchmarking, they would do studies of optimization, and then they would feed that back to the architects of, hey, these are the things we care about that do well on these we think project are going to do well. These are the things we think don't matter as much, right? And the one thing that they said, the first order bit was, while the applications were not monolithic, two things we could say. Apps were typically limited by memory bandwidth, even in the context of a chip that didn't throw a lot of flops into play, right, in Haswell. And the capacity growth of memory was outrunning our application needs based on the roadmap we were looking at the time. We were adding more DIMM channels to add more bandwidth to solve the first problem, to go with core growth, but at the same time, adding more DIMM channels also mean we had to buy more capacity of memory in order to get the same, to reach the bandwidth we needed, right? And that was starting to actually significantly outpace the amount of memory we needed. That's bad. And then you say, well, you got extra memory. What's so bad about that? What's so bad about that is you had to pay for it, right? Memory turns out to be expensive and getting more expensive, right? So that was an issue. So we wanted to set some goals, right? What are we trying to hit? Well, let's assume we want to hit a bandwidth to flop ratio of about 0.2. And this is, again, the view from 2015 about what we were trying to target, right? So 0.2 bytes per second per flop. And so then, okay, let's look at what memory technologies were available to reach those system level ratios and that were common in 2015 or we were looking at, right? And the other question is sort of what are the limiting figures of merit? What are the figures, the quantitative measures we care about, right? So the first one is going to be, we're looking at bandwidth delivery. Well, these exascale systems had a power boundary, right? We wanted to fit within 20 megawatts to get an exaflop in 20 megawatts. Okay, let's look at power, right? If we want to deliver 0.2 bytes per flop, right? That's just 200 petabytes per second. You can do some very quick math to go, if I had DDR4, how many DIMMs would I need to deliver that much bandwidth, right? And how much power do those DIMMs use? And the answer is, to deliver that much bandwidth with DDR DIMMs was about 50 plus megawatts, right? Just simple math, right? Which, of course, tells me that this is without computing anything. This is just media power, right? We aren't even looking at compute elements. So this was obviously not the answer. We needed to start looking at alternatives, and so we were working on some of those options. HBM, as you can see, falls well below that, right? Now we got almost an order of magnitude in power efficiency from HBM. That gives us this really nice, almost 10x in power efficiency. Hey, now we're at like 7 or 8 megawatts of memory power. Now we can actually afford to compute something, right? One thing that's not on here, by the way, is hybrid memory cube, which we were looking at the time. And that one kind of falls in between these two because it was like high bandwidth memory in some aspects, but it also tried to be sort of DDR-like in some other aspects. It added an intermediate layer that reduced the efficiency, but made it more flexible. And what we found was it made it more flexible, which also made it more expensive and not as good, right? And so if you can use HBM, it was the ideal way to approach this. Now, the other metric for building the systems is dollars, right? Or pick your local currency, right? In our world, it was dollars. And if you look at the amount of money it costs you to deliver 200 petabytes per second, HBM is also 10 times cheaper. And you would say, well, why is that? The answer is because we were overbuying capacity of DDR memory. And you can get a much better deal, a much better bandwidth to capacity ratio with HBM, right? Now, it's on the low end of the capacity curve of where we would like to be, but it's a feasible amount. But in that vein, and by the way, we also evaluated things like Optane, right? Storage class memory. It turns out the bandwidth per watt and the bandwidth per dollar was another 10x worse than DDR. Right? I didn't put it on this graph because you wouldn't be able to see the rest of the graph. Right? It was horrible. And this seems, for us, it seems kind of obvious. At the time, all of the fast forward to, like RFP was talking about these multi-tiered memory systems with these big storage class memories, right? And what we effectively proved was that that's nice, but you can have that memory, but you can never actually use it, right? And so what point is there in having it? So we're all associated with architects here. Why not combine two memory types to get the benefits of both? You get the capacity of DDR, you get the bandwidth of HBM. Why not do both, right? Oldest architecture trick in the book. Add a layer between two types when there's some pressure, right? To manage gaps in that need. And so we evaluated that by the same two metrics, right? So if you look at the same kind of quantification of bandwidth, what's interesting is that we wrote this as sort of what percentage of your memory traffic would have to go to each level of this memory, right? So you have an HBM tier and you have a DDR tier. What percent, what's your hit rate effectively, right? And then what's the power for delivering the bandwidth to meet that hit rate, right? If you look at 90%, which is, 90% of your bandwidth comes from HBM, 10% comes from DDR. Whatever scheme you want to use there to manage that hierarchy, ignore that for a minute. Let's assume we achieve this goal. that would be about 11 megawatts. So it's like almost 50% increase. And by the way, this also applies to cost. Bars look very similar, right? To get this added benefit of a 2-tiered memory, right? But you had to hit like 90% hit rate. So then, hey, let's go look at the next level of the performance aspects of the workloads and see, is a 90% tiered memory hit rate feasible, right? And so what we want to look for is this hotness density in the applications. So we didn't do that. Now, to just sort of explain this graph, we took a number of these applications we were working on, and we ordered the pages here from most accessed to least accessed, and this is a cumulative distribution, right? And so what you can see in this case is, excess bench, the green line at the top here, it over the course of about 18%, the top 18% accessed pages made up over 90% of the accesses, right? So that tells me from a capacity standpoint, you could take 1/5 of the capacity and you could achieve 90% bandwidth out of that 1/5 capacity, right? This to me says, hey, tiered memory probably works, right? However, that was really the outlier. And this is what we learned from also talking more in depth about the full workload sizes, was that level of sort of tierability was very indicative of how excess benches data structures were set up, right? There was this very high density search structure, and then there's a big data set that it goes off into at the end of every pass through that first part, right? The others were not like that. It was much flatter, a lot more, more regular data distribution. And so the ratios did not really align with this very hot versus not hot zones, right? So does adding a DDR tier add value? The application analysis said anything worse than about 5-to-1 bandwidth ratio is going to really get hurt by DDR, by this tiering and having to go to DDR, right? Now, there's a separate conversation about using a second tier memory for something not application related. But, working through this, directionally, we said we should really shoot for a mostly single tier memory that's based on high bandwidth memory. So where did we end up? Interestingly, Frontier's ratio in this regard is 64-to-1, right? And I should add the capacity ratio is 1-to-1, right? It's about 512 gigs of DDR4 per node and 512 gigs of HBM per node. And that DDR is not really for much other than file system cache, right? It's effectively there not for application purposes, but to host the OS and storage, right? So not all data points are performance, right? And I mentioned RAS earlier, and resilience and reliability. And actually, I want to just call back to another talk actually hosted by Owners Group. And it was Siddhan Gurumurthy maybe a few months ago, where he talked through the work that they did on the HBM3 error codes, which is sort of an industry collective action to try and improve the resilience of HBM for generation 3. And this was really I call this talk out. It's great to go watch because it's very data driven, right? They went and found what are the requirements for the level of RAS to keep a system up, which a lot of those came from us, right? And then what were the sort of pieces of the architecture that where you could apply bits to try and minimize the number of failures. It was based very data driven way, and it's a great talk to go check out. Okay. So that's sort of the data-driven path we walked down for the Exascale studies, moving into the sort of evaluation and architecture for the actual systems. I want to flip over here to another set of problem statements and try and look at some similar kinds of approaches, right? In this case, this is from the last couple years, looking at resource management in cloud data centers, particularly around memory, and again, taking a data-driven approach to how do we want to architect things, to give us the best advantage, right? So I went from working on large-scale computers to a different kind of large-scale computer. This is some pictures of our Dublin data centers. It's a great data center site from Microsoft. These are DB3 and DB4. You can kind of get a feeling for how big they are. There are some, cars in the parking lot, right? These are not small buildings at all. They're multi-floor. They got big chillers on the roof, right? Big data centers, okay? This is DB3 and 4 with the new data center DB5 that came maybe a year later. A year or two later, this is 3, 4, and 5, and now here's 6, and here's 7, and here's 8. And by the way, we're not done, right? And the way I would put it is, I don't know exactly where we are on this, how this is probably out of date already, right? But the very first one of the Dublin data centers was built in 2012, right? So this is 10 years of growth, right? And again, it's continuing. On top of that scale, locally in Dublin, there's of course the fact that we have data centers all over the world. We're adding new regions all the time. This slide is probably out of date. Hey, we have a region that's actually on the surface, the floor of the ocean, right? But all of these regions have to serve a lot of different pieces of computing to a lot of different people. And it creates some very interesting resource management problems and architecture problems that feed back into the fleet. So here's some, cloud architecture problem statements, right? Diversity everywhere. We're trying to sell a more diverse set of compute VMs, more options, more architectures. The diversity of different types. So that's the software view, right? The sales view. And then in the hardware side, we also have a diversity of configs, right? We have, different CPU options. We have new accelerators. We have, entire HPC clusters, right? Especially at Microsoft, we very focus on verticals. And so we go after some very specific verticals with very specific hardware requirements. Some of these landing configs are even becoming mutable, that you could actually change where resources are. This is sort of a circular reference to something we'll talk about in a minute. And the dependency models between things are also increasing. And so there's these cross requirements of one talking to another. And lastly, this is all done in an environment that's enterprise class, right? So online messing around with new capabilities could impact millions of people, right? You're all running something on Azure services, whether you know it or not, right? And so, don't test in prod. We're not going to go do something. We have to walk a very careful line to make sure that we're providing the same service level that we're supposed to, right? So all this kind of feeds back to us of like, how do we manage all this complexity? Because if we have a diverse set of things, we have to deploy this in every region. And that sets some really high bars for what a minimum sized region looks like, right? How much do we have to deploy in each place, right? Those kinds of things. So let's look at memory specifically. And what is the state of sort of what I would call general purpose public cloud memory, right? One, it's becoming the largest portion of server costs. Basically, CPU core count's going up faster than we're able to scale memory capacity. And so as a percentage of the server cost, it's going up, right? It has been in the 20s or 30s, and is soon going to approach the 50% range. Like half of what we spend is memory, right? What sort of rubs salt in it is, of course, often that memory isn't very well used, right? We have it, but nobody's using it, or is using it, or it's not being allocated, right? First order thing is up to a quarter of our memory is what's called stranded, which means that there's not any free CPU cores on the node, but we have extra memory that's not sold, right? And we have sort of done analysis on that, looking at collections of clusters in the fleet of, as we, schedule CPU cores on different nodes, the amount of stranded memory, kind of hardens up and becomes in a number that's in the 20s of percents. So memory that we just can't even sell to anybody, but we have to have. Right? Interestingly, our customers also over provision memory. Now, part of this is by definition, right? If you buy a VM that has 6 gigabytes of memory, you're going to use strictly less than 6 gigabytes. Turns out, though, that most people use a lot less than their reserved amount. And the median VM uses almost half of its memory is untouched. Right. So we've got memory of which a quarter of which we can't sell. And even amongst what we sell, almost half of it isn't really being used. Right. And so there seems, from everybody looking at this, a really big opportunity for how do we approach being more efficient with this. Right. This is a lot of over provisioning of memory. So there's a new concept in town called composable disaggregated infrastructure. This is sort of the IDC definition, but it effectively means that if we have resources that are within the silos of a server, we have to provision enough for the worst case. But we often are left with extra, right? Composable infrastructure, the idea is by adding a little bit of connectivity, we can share those resources amongst servers, and thereby we can provision for a worst case, which is we can basically shrink the peaks of the curve and serve the high end of things, but rely on sort of statistics to not have to serve the highest thing on all of them at the same time, right? So we're going to basically use that to help reduce the amount of stranding that we have out there, because we don't have to over provision quite so much in this sense, right? So the benefit is avoiding worst case provisioning. It's a more efficient use of capital, right? And so specific to memory, here's kind of what it might look like, right? So we have a certain amount of provisioned memory capacity. It's often underutilized, right? Now, we can't just deploy less because sometimes we need all of it, right? We need that full amount. So if we don't do that, we either strand cores, which is not good, or we actually chop off workloads that could be served in our fleet, now it can't be, right? Full node BM kind of things, right? So the approach of memory pooling, which is the version of disaggregation we kind of were looking at, is to go ahead and deploy less on all of them, but then deploy a little side amount that handles the variance, right? Handles those worst cases such that we can deploy in total less and still handle the sort of worst case scenarios, right? So this is the promise of it. Right? Okay, so super simple idea, share stranded memory with nearby servers that have free cores, and you can kind of move that back and forth. It becomes somewhat fungible. So we need to be data driven. What do we care about? We went and did some analysis of a scheduled segment, a big chunk of our fleet, and said, if we had a certain percentage of the memory of these servers in pools with its nearest neighbors, how much better would we have done and how much less memory could we have deployed? And so we looked at this at a few separate percentages. So if 10% of the memory was in the pool, or 30% or 50% of the memory was in the pool, right? And we found that you could save, 5% or 10% less memory. Right. And at the amount that we do memory, that's a lot, right? That's real money. That's maybe the way to put it, right? This sort of says, though, that even small pool sizes, and the x-axis here is what we call pool radix, right? What's the number of CPU sockets that the pool extends across, right? We don't have to go very far, 8 or 16 sockets, and see a benefit, right? What's interesting is if you go back to the triangles at the beginning, this does not fit the triangle model, right? The pool here, which is a slower tier of memory, slower because of being on CXL, it's smaller than the main memory, right? But that's because we want to focus the performance on the main memory, use the pool only for variance, right? It's not a traditional caching model where you want the big and then you bring things in, right? This is a sharing model, which is different. The challenge here is managing performance. And so how do you make sure that now that we have a hybrid memory, somebody doesn't land in a really lousy piece of memory and get bad performance and then call us, right? That's the phone call you don't want to get from infrastructure, right? Is keeping our service levels up. And so we've done some exploration of solutions. There's the paper it got posted as a preprint last year and got some attention, but it's actually being presented at ASPLOS in a month or so. So you can go check it out. We'll give that presentation. And that really focuses on how are we using, what are our requirements for memory in the cloud, and then how do we use our potential knowledge of what's happening in the cloud to manage those trade-offs. So CXL, by the way, is a great and evolving interface to enable more nuanced expansion, sharing, disaggregation solutions to move into the memory space, because disaggregation has been around in storage, for example, for quite a while, right? So CXL covers a lot of ground, and the spec as it stands today enables a massive design space of solutions, right? Now, I would contend one of the parts of my job and my group's job is to figure out which of that massive design space of solutions is actually useful for us, right? But back to the what do our workflows look like? How can we architecturally do something that's beneficial for that? Right? So you really need to know what your workload needs. And when evaluating these solutions, by the way, more flexibility is not necessarily better. In this context, more flexibility often equals more cost. And so what you end up doing is overburdening what you're doing in a way that doesn't help you, right? You want to avoid that. As an example of that, there are two ways that are sort of publicly discussed about memory pooling architectures, right? One is what we would call a multi-headed SLD. This is, this definition is given in the CXL3 spec, which is effectively you have a memory device that has multiple ports that are connected to multiple hosts, right? But it's directly connected. So you'd have an N-ported controller going to the N hosts, and each one has a direct connection. And so, but the memory within that, within that device can be assigned to one host or another depending on need, right? So there's your fungibility, and this architecture has some pros around latency in particular, but also around cost. On the other side is switch attached, what they call, SH single-headed multi-level device. Multiple logical device. You get my definitions right. And in this context, you would put a switch here, and then the hosts would connect to the switch, right? Or a fabric of switches, and those switches would hang off individual devices. That the sort of the connectivity graph would be implemented by the switch instead of as a direct connect sort of architecture, right? These are two different ways. They have sort of pros and cons, right? Direct attached multi-headed is lower latency. It has some trouble, of course, with scalability because you're limited to how many ports are on your devices, more or less. And there's some cabling challenges of getting that to set up. Switches, on the other hand, more scalable, more flexible, but higher latency. There's extra devices, so you have more cost and power. And there's also benefits from a RAS perspective about if you lose things in this environment, you have more resilient paths, right? So how do we decide what's interesting, right? So when you see people talk about disaggregation in public forums or trying to sell you something, they'll focus very heavily on what is the improvement you can get in efficiency from having a disaggregated thing, right? So they'll say, yeah, you can spend less on COGS, it'll lower your power. There are other things you might care about, right? Sustainability, durability, all this stuff, right? That's your benefit from disaggregation, as we talked about, being more efficient with your resources, right? It's always worth remembering that what you're doing, if you remember back to the CDI graph or picture, is that you're adding connectivity, right? You have maybe fewer resources, but you're adding connectivity. And connectivity is not free, right? So there's a cost to that disaggregation, right? Which may weigh on cost, may weigh on power, may weigh on performance. And we have to figure out where's the balance point on these, right? And so then you say, well, what is the metric that I care about the most? And how does that balance across sort of the efficiency of the improvements you're getting the benefits versus the cost? And this is a little more complicated metric than we were dealing with sort of in the bandwidth case, right? In the power case. But, in a general sense, I want to be clear, what I'm about to show is our view of a specific use case, right? But that may not be the same set of metrics or results that somebody else might have for their workload. So I'm going to put that out there as a clarifying statement before I get into that, right? So our metric that we used was, let's just start by weighing the dollar benefit versus the cost benefit, right, of different pooling architectures, right? And the way we looked at this, and this is from a new paper we just came out with, is we looked at constructing pools out of multi-headed devices, and we looked at constructing pools out of switch-based systems. And then we gave some very simple cost models to those systems, including the silicon, the memory itself, the rest of the system, and the connectivity you need to add, and the infrastructure overhead you need to add in order to build up these pools, right? So there's, right, you need an extra dedicated place to put the memory, you need connectivity by cables or whatever mechanism, right? And then, stuff like fans and other pieces of infrastructure to deal with this, right? A couple things that fell out of this, right? So if you look at a case where we have, say, 25% pool memory, right? So if you can think of, if we start from all memory is local, and then we say, let's design a system where 75% of our memory is local and 25% is in the pool. And then we look at the deployment benefit of that. And from that graph earlier, right, where we looked at, hey, if we have 25% of our memory in the pool, what percentage of reduced amount of stranding are we going to get, right? So that on these graphs is the black line, right? That's right, this line, that's our benefit. Now, what you'll notice about the benefit is most of the benefit is in the first number of, and this is again against pool size, pool radix, right, is in the first few extents. And I think the reason for that should be pretty clear, is that you get these fungibility benefits. You really don't need that many servers to get a lot of that benefit based on the variance of the workload, right? And so you capture most of that benefit in the first amount of pool. What you might also notice then is the implementation costs of those things, which start out having a few percent overhead, but as you increase the pool size, start to go up and go up a lot. And the reason for that is as you hit these larger sizes, you have to convert to a switched network. There's really no way around it. You have to go to a multi-level setup, right? Even with the multi-headed devices, you can delay that further and then go up, right? In this context, the solid lines are the switches, the switched view of that based on the SLDs with switches, and the dashed lines are the multi-headed devices, right? So, right, two basically results out of this. Any pool size or any implementation beyond about 16 sockets would likely add cost faster than the benefit that they add, right? And for memory pooling, the switching, adding that flexibility of switching will generally, from our view, overwhelm, in our use case, potential benefits, right? There are other uses for those kinds of switches, but in the context of what we're looking at, it doesn't make a lot of sense. Right? You can read a little more about this in our paper, which is, I think, up now on IEEE Explore. It's published in Micro. And it talks a little bit about some of this modeling and the trade-offs here. But really what we're thought, if you're looking for a place that's useful, right? Right now we've identified this lower part, right? Which again points back to our first paper. We're looking at small pools and trying to make that as manageable as possible. I just want to step back a second to talk about disaggregation in general outside the memory context, because this is coming up in HPC world a lot. And honestly, if you look at a chart of different technologies, right, memory and storage in particular, and you kind of look at them on a latency and a bandwidth chart, like I have here, like what's the required bandwidth that we would typically provision for this, and what's the latency requirement for how we use this. Disaggregation has costs, as we mentioned, right? And at a high level, if you go up in this chart, meaning more bandwidth, well, there's an old phrase I like to fall back on, which is bandwidth is money and latency is physics, right? So if you go up on this graph, it's more expensive to disaggregate, right? Try to provision HBM bandwidth with Ethernet, right? Physicals, right? As an example, right? A very gross example, right? But if you're moving left on this graph, you are seeing perhaps media things on the left of this graph will see a bigger impact from latency because they're used to a low latency, right? And so what this naturally falls into, by the way, some people, first of all, will tell you that there are disaggregation solutions. It's one size fit all. You can put memory on it. You can put accelerators on it. You can put whatever, NICs. It doesn't exist. You're going to pay for it in one of these zones or another, right? And you can kind of define domains here of where you might be able to do disaggregation based on these parameters. It's something to think about, right? These are not canonical zones, by the way. It's sort of crudely drawn, but as an example, HBM within the package, if you want to disaggregate it, well, it turns out you can kind of do that, right? You can split it up into multiple pools, but it has to be in package, right? However, DDR, you're able to go a little further, right? Physically, it's more tolerant of that from a bandwidth perspective. Latency-wise, they're fairly similar, but so you want to maintain a pretty short connection, right? And you can kind of take this out as you go, right? What's out in a rack and what's on a real global fabric. One thing that's not on this graph, by the way, is accelerators. And the way to say, well, where do they go? They could go anywhere, right? There's going to be some accelerators that go in the top left because they're embedded in your SRAM accelerators, right? There's in-memory compute stuff. There's accelerators that, if you want to think about Project Brainwave stuff, it's bottom right, because from a physical standpoint, it's extremely latency tolerant and it uses almost no bandwidth, right? In that context, it's inference designs. So just a thought process. In disaggregation, you have to run this trade-off and you have to think about your available disaggregation domains so that you understand those trade-offs of benefit versus what the cost is, right? Okay, so sort of to sum up and take takeaways, right? Memory and storage are often drawn as triangles, right? But if you're adopting a technology, you need to drive it by workloads needs and not rules of thumb, right? You can get yourself in a lot of trouble just doing what you think everybody else is doing, because you could end up really hurting yourself from a sort of price performance perspective or any other number of metrics, right? Measure your goals as close to the workload as you can get and use metrics that matter to your system level goals. Don't worry about the local, tiny, short-term, minimal, requirements goals, right? Worry about the system level, right? Because that'll guide you in the right direction numerically. So from the two case studies for HPC apps, HBM has the right performance to capacitor ratio. It actually made our system cheaper, right? Not just more performant, but cheaper by using the right memory. And then disaggregation, this is a really interesting field that's worth studying. Measuring how disaggregation, that cost benefit balance, is super important because blind adoption of disaggregation can cost you way more than you can save, which doesn't mean it's not useful. You just have to know what you're doing, right? You have to pay attention to these metrics as you're developing systems like that, as you're thinking forward. So with that, thanks for having me, Torsten and Martin. I appreciate the invitation and happy to hang around and take questions for a while.
Thank you.
Thank you very much for a great talk. Just a quick announcement. We invite you all to the next SPCL BCAS happening in 2 weeks on the 2nd of March, where we will host Abhinav Patel from University of Maryland. For questions, everyone has 2 options right now. Either you can raise your hand and then I'll ask you to unmute yourself, or you can put questions into the chat and I will read that. So I can already see that Torsten has the first question. So
So I will ask the unavoidable CXL versus everything else question. So it's actually 2 questions. So you mentioned the single-headed CXL3 thing, and I'm wondering if we can now communicate between hosts. such that you would actually have a local high-speed interconnect that CXL could be. And then as an extension to that question, if that is true or not, how would that compare to inter-node interconnects such as Ethernet or InfiniBand? Are we looking towards convergence or reusing technologies? I mean, even at the physical, they're somewhat different. So what is happening?
All right, two fantastic questions. So first to the, can you use it as sort of a shared domain is maybe the way I would put it. Interestingly, when I've talked to our database people about pooling and the benefits of perhaps having fungibility, the first question they ask is, can we use that as a way to do a bounce, right? Because they want to do synchronization, for example, or a sort of a producer-consumer kind of model for different pieces of database queries. And they would prefer not to have to go out through the front end, Ethernet stuff that's going to be a lot longer latency, right? So I would say in the CXL spec, the 3.0 spec supports fairly well supports shared memory regions within devices, so that you can actually have them as shared memory with some amount of coherence support. You could, there's nothing that would stop you from building a device that exposed a region to multiple hosts and sort of, handed you the chainsaw, right? You can go ahead and do your own software managed coherence, right? But there is definitely some use cases we're looking at of is there benefit to doing some amount of communication through that channel as a way to avoid a longer latency thing, right? Think synchronization, think reductions, that kind of stuff.
But that is now still a point-to-point channel from host to memory and from the other host to memory or to device.
That's correct.
There is still no direct communication from host to
so
host.
then you're there's a direct communication by way of right memory in between the two of you, right? But,
well, it's not very direct.
yeah, it's not very direct. Now to the sort of follow-up, which is, hey, can we build a fabric out of this? There's like 4 different answers to that, right? So you can build fabrics out of CXL3 where you have multi-level switch hops, right? But that fabric setup is based on the protocol very, very much not set up to do host-to-host communication. It's not really, you can do it, but it's got some oddities to it, right? The way that the protocol supports different types of pieces of it, right? I think in the long view, it is not trying to be a new InfiniBand, right? Or a new, slingshot or whatever. It's trying more so to be, it's moving from a place to attach memory and accelerators that's better than PCI Express, right? That puts you into the memory domain. And it's trying to be able to stretch that towards perhaps being something that looks like an NVLink kind of network, where you have sort of a let's call it a coherently local or semi-coherently local memory semantic fabric, right, to do exchanges. In the long view in the HPC world, I do not see this growing into the next InfiniBand, right? And the reason for that, a lot has to do with the whole load store thing versus put get, which is a discussion about how you actually move data, right? Load store is great from a software programmability standpoint for existing things, but from a scalability standpoint, it's very intolerant of variable and long latency, right? And so you have to have a level of indirection. This is what the Cray networks all do, right? We learned that lesson a long time ago, right? The hard way. So, that's sort of the difference, right? There's definitely an aspect of fabrics, and there are pieces of the CXO protocol that'll let you do interesting things like moving data between accelerators and memory that's sitting out on a fabric directly without having to go through a host, for example. So there's a lot of development of different architectures possible there. Like I said, the diversity of options is huge, right? It's just a matter of finding the ones that have interesting benefits. Great question, though.
Thank you. Thank you.
Do we have any other questions?
So then I have one more if there's no other question. So now we've been talking a lot about memory and also the relation to networking somehow. I mean, you brought it up yourself with the CXL, which is like a mini network. Would we see and you mentioned this memory hierarchy at the very beginning. And now we do disaggregation within a rack essentially, or within a small group of servers. But would there be use for another level of disaggregation, which would be like network-wide disaggregation or something like this? Because we have disaggregation at the very bottom. Storage is disaggregated. Like we've been doing this for decades in HPC, and now slowly data center providers are like, yeah, let's do that as well. And now we're moving disaggregation to the very top in memory. So is there a middle tier? Something like burst buffers come to mind, but
Right,
the NVMe maybe. But is there something in the cloud that would make sense where we would disaggregate with a wider group, or do you think that that is not useful?
Yeah, if I kind of go back to the this picture, right? This, SSDs, right? Storage in general, that disaggregation of that I think is well understood and is done in places, right? And it's being done in more places. For generally quite good reasons, right? There's a lot of over provisioning there too, right? NICs I have on here is an interesting one because again, the latency requirements aren't quite DRAM, right? I mean, if you're not doing financial trading, right, then the latency requirements are more microsecond scale as opposed to nanosecond, hundreds, tens and hundreds of nanosecond scale, right? And so that could tolerate some amount of indirection, perhaps some of these high-speed switches. So CXL switches could be able to do 100 nanosecond, right, cut through, right, or less. And so in that context, putting a NIC in a way that's disaggregated, or you would have multiple nodes and multiple NICs that are sort of shared across the CXL fabric, is something that might be feasible, right? And again, you have to weigh it against how you use those NICs, right? Are they heavily utilized for every local thing and you need a very balanced, jitter-free network? Maybe you don't want to do that, right? But are these things that are fairly lightly used, but you do want low latency? Maybe you're able to do that in order to, again, reduce over provision, right? The ability to do sort of multi-host support on NICs, I think, is going to become more important in a general sense, just because the idea of balancing node architectures with NIC speed is very hard if you only have one NIC, because nodes, there's lots of different nodes, and some of them need a ton, some of them need very little. And you want to be able to not have to slap a really expensive NIC on all of them, right? So can you share them? Are there ways to disaggregate? I think is an interesting space as well. That's a little more open-ended. Accelerators is another one, right? And particularly as you start looking at trying to do inference in the middle of all your other workloads, there's plenty of opportunities to place, for example, inference devices within your fabric in a way that make them shared and available to anybody that needs them, but you can independently scale it, is sort of the idea, right? So those are some of the spaces where I think in particular this has got some good legs, disaggregation in general. But I agree with your general point, which is underlying that, which is it's probably easiest to start from the bottom right and move up and left, right?
Yeah, thank you.
Great. We have a question in the chat. So Johan asks, thanks for your great presentation. You made a point about being workload dependent in your use of memory. In Azure, how do you deal with not being able to know what workloads are running in customers' VMs and still make clever decisions about memory usage?
Yeah, that's a great statement and a great question, because we're very, very committed to the privacy of our customers, right? To the point of we are, almost sort of pathologically, we're moving towards a confidential computing future where we're trying to have everything encrypted and isolated even from us, right? The hypervisor and the host can't even go poke in things, right? What we do know, what we can gather, is things that are visible from outside the VM, right? Envelope. So, for example, how many, the underlying memory manager can observe what pages that were given to this VM, right? If you go look at the access bits, for example, which ones were touched, right? You can do some access bit scanning as an example, or you can go run socket level telemetry coming out of the L3. How much bandwidth are we using, right? So there is some amount of data we can get in terms of observed resource usage. Is the way I would put it. It's not about what's actually happening in the virtualized environment, but it gives some idea of resource utilization. And so that is the kind of critical piece if you're looking at what we're doing around memory pooling, trying to get requirements for memory, right? We have to rely on, and by the way, we much prefer to rely on fleet data rather than people's rules of thumb, right? We have to, we need to get at least X gigabytes per second of core bandwidth, right? Well, what's that requirement based on? Let's go look at the fleet data. Do we actually use that? Does anybody actually care? Let's go look at it, right? Having that data is important. So that's a great question because we have to balance that carefully. We can't go look at what they're actually doing, but we can observe some stuff around the edges of the resource utilization.
Great. Thank you. Johan also thanks in the chat. Do we have any other questions? It seems to me that not. So thank you again for being with us. Thorsten unfortunately had to run, but thanks again from both of us, and hope to see you all in 2 weeks in the next Bcast.